Hi, everybody. Welcome to the Khronos Group's OpenVX webinar. We have a good presentation for you today. We are going to have presentation from Kari, Pulli and Radha, Giduthuri. They are both working group members on the OpenVX working group. We also have Frank Brill, also from the working group, who will stick around and at the end help us answer questions. If you have questions during the presentation, you'll see in your GoToWebinar interface there's a question mark icon. You click that and that will let you submit a question. Frank will answer questions during the webinar for the most part, but some he may leave till the end. Stick around to the end and we'll have a QA session as well. All right, and with that, I'll turn this over to Kari, and then when he's finished, we'll turn it over to Radha. All right, Kari, thanks.
Okay, thanks, Kathleen. So good morning, everybody from the sunny California. My name is Kari Pulli. I work at Intel, and I'll start with an overview of OpenVX. OpenVX is a standard API for computer vision created by Khronos. Khronos is an open consortium that creates standard APIs for hardware acceleration. A large number of companies come together at Khronos to create APIs that make accelerators for graphics, compute, and vision processing easy to use. Real-time computer vision requires lots of processing. Just using CPU to process all those pixels becomes too expensive and requires too much power. Especially on mobile battery-powered devices, the battery would run out too soon. Most devices also come with a GPU, which is a much more efficient pixel processor than the CPU. And many digital cameras, in particular camera phones, come with a dedicated processor called ISP, which stands for Image Signal Processor, and this is even much more efficient than the GPU. But there hasn't been a standard way of programming specialized computer vision processors in a way that would allow the same or almost the same program run on systems that come from different manufacturers, that is, provide some performance and functional portability. OpenVX is a new API for low-power vision acceleration. It is a fairly high-level API for the C programming language. Its purpose is to provide real-time computer vision support on mobile and embedded devices. The API abstracts the underlying hardware. The implementation can use multi-core CPUs, GPUs, DSPs, ISPs, FPGAs, or some dedicated computer vision hardware. The programmer doesn't need to worry about exactly how the tasks are distributed. The device manufacturers take care of those details instead. Each subtask can run on the most power-efficient hardware the system has. If there is special ASIC for some task, the system selects that unit instead of the very general but power-hungry CPU or GPU. Algorithms that run efficiently on vectorized integer-based vision DSPs run on those. Tasks that cannot be run on the most efficient units can be run on the GPU or CPU, but if a better unit is available, those more general processors can even go to sleep to save power. A key idea in OpenVX is the concept of organizing computation into graphs. Nodes in the graph process data, typically pixels, and they may run on different processors, depending on the processor capabilities and the current system workload. The application first sets up a graph, telling the system in advance which type of processing it will want to perform. The system then can optimize the total graph before executing it. The host, that is the CPU, needs only pass in some data and then can idle while the OpenVX subsystem autonomously executes the graph. There are several sources for the efficiency of the OpenVX framework. First, there's the scheduling of the graph, which allows the system to split the execution of different parts of the graph to different processing elements, allowing trade-offs such as faster execution or lower power consumption. The OpenVX objects are opaque, which means that data can only be accessed after explicitly asking for such access. And some memory objects are only virtual concepts and can be even optimized away. The system has more possibilities to cleverly reuse memory, yielding both faster and lower power execution. Since the system sees into the future because the user prepares the graph and the system sees the graph before executing it, and sees which operations are going to follow which other operations, it can merge kernels. Instead of processing every pixel of an image with kernel A, storing intermediate results, and then processing those results with kernel B, the system may do both kernels at once as it iterates over the pixels. This can yield huge savings, meaning much fewer memory accesses, better memory locality, and smaller kernel launch overhead, as fewer kernels need to be launched. Finally, by tiling the image, one can further increase data locality and benefit from better caching behavior. More importantly, imagine that the accelerator may have some local memory, but not enough for the whole big image. If the input is split into tiles, it might be able to process kernel after kernel over this tile, keeping all the data in a local buffer, and avoid all expensive trips for the intermediate data to go back and forth in the main memory. After one tile has been processed, the set of kernels can be applied to the next tile until the whole image has been processed. Lots of people ask, how do OpenVX and OpenCV relate to each other? OpenCV is a very extensive open source library that has thousands of imaging and vision functions. It was originally created for CPU, first for the x86 family, but is now available also on ARM, and parts of it can be run on a GPU. But its model of exposing all the data to the programmer and its model of calling functions synchronously, one at a time, makes really efficient hardware acceleration difficult. OpenVX has a smaller set of functionality. Its opaque memory model and graph-based execution give much more optimization possibilities. In the future, once OpenVX is widely available, it might make sense to build OpenCV on top of OpenVX. The version 1.0 of OpenVX was finished almost 2 years ago, and it came with an open source sample implementation and conformance tests. Version 1.1 was released last month, and it has enhancements to the node functionality and the graph framework. The specification spells out which functionality has to be included, but the vendors may extend the API by vendor extensions to meet specific customer and market needs. And popular extensions become candidates to be included in the core spec at a later version. At the moment, there are 8 companies that have already provided results for conformance tests. So that means that they actually have a working implementation. And at least 2 of these companies are already shipping an implementation. So this is last slide of my part. Do we have any questions in the meanwhile? Okay, so maybe we'll move over to Radha.
Good morning, everyone. My name is Radha Giduthuri. I'm a design engineer at AMD. In this presentation, I'll go over the basic concepts of OpenVX APIs. Please visit khronos.org/OpenVX to get access to the specifications. There are discussion forums there and other OpenVX related resources. Some of them Kari has hinted in terms of our sample implementation. There is also a link to tutorials there, And there are other implementations that are available. There are some open source and commercial implementations available. You'll find links to all of that on the website. Give me a second. Yeah, okay. So OpenVX components. Let's start by looking at various components of OpenVX framework. Everything in OpenVX starts with creation of a context that is used for managing objects and executing vision functions. To deal with several types of data objects used by various computer vision algorithms, we have defined few opaque data objects that are listed here. You can see that VX image for images of various single and multiplanar formats such as RGB, YUV, and 8-bit unsigned 8-bit values or signed 16-bit and various other. There are about 13 different formats that are available there. And VX pyramid for image pyramids which contain collection of images with different scale factors, and similarly there are arrays for array of built-in data types such as integers or some other predefined things such as key points or rectangles. It could even include certain user-defined data structures in there. And there are several other data types such as lookup tables, remap objects, scalars. If you want to use such as floating point or integer values, you could use a scalar object in there. And there is threshold for thresholding kind of functions. There's distribution for histograms, matrix convolutions for doing transforms and image filtering kind of operations. There are certain high-level container data objects such as delay and object arrays. We're going to cover some of these throughout this presentation. And next part is kernels, which is kind of OpenVX abstracts the vision functions using VX kernel objects. It basically includes 44 standard built-in functions. And some vendors and third parties can supply their own additional vision functions, and they can be uniquely identified by a certain kind of enums that are specific to the vendor. And users can also wrap their own IP into OpenVX kernels and use it from within OpenVX framework. It's kind of pretty flexible from that perspective. Now let's look at graphs. Graph is kind of a set of nodes connected in a kind of a direct acyclic fashion. And what it gives you is for a framework to optimize a computer vision workload by fusing functions, optimizing data flow, and schedule to the points that Kari was mentioning earlier. A node pretty much is kind of an instance of a computer vision function, and it gives the linkage to other data objects that are available within the workload. Now, in a typical graph, you'll find several kind of intermediate data objects. Mostly, application doesn't need to access these ones directly. Means you don't need to access the physical data memory of these objects, and they can be created as virtual objects within OpenVX and keep it within the scope of a graph. So what gives that? This gives the flexibility for an underlying framework to kind of optimize it or reuse a set of memory, kind of reuse the memory for various kind of operations within that. This further helps the graph level optimizations in that. OpenVX also has other miscellaneous features such as performance measurements, logging, hints, and directives that we're not going to cover, but I think you'll find a lot of usefulness during the debugging and profiling your code. And there are extensions, provisional extensions available for tiling and XML schema that you can access from the Khronos website. And you should watch out on our website. You'll find a lot more extensions, provisional extensions that will be coming through in near time. Before you can do anything else, you need to create the OpenVX context. A context is stored in a handle that later needs to be passed to other OpenVX functions. Here is kind of an example where you kind of see all the APIs and the data types. You can access them using the vx.h header file. That's a common, which further includes other header files such as vxapi.h. And once you include that, you have access to all the functions and the data types available within the OpenVX. So in this particular, to create a context, you simply call vx create context, which just returns a vx context type that you can use. Now, error management. This is very important. Many OpenVX calls return a VX status, which is kind of an enumeration. If this status is equal to VX success, then we are good. If not, you got to deal with the error situation. Some methods return a kind of VX object, such as if you see in the VX create context returns the context object here. And since C only allows you returning one thing, you have to separately get the error code in case if the object creation fails. So you can pass that object to VX get status function, which will return VX success or failure, or one of 24 other error codes, giving you a reason why it failed. So you could use that error code to kind of do some kind of error handling in there. You can also register a log callback function that will allow you to get more information from the implementation as it processes your VX calls. We're not going to go detailed, but I just going to mention that one here. So it's kind of a very useful feature in there. And if you want to look at more details in terms of what are the various types available, error codes available, look at vx_types.h, which can have all the list of the error codes in there. Data objects. OpenVX uses opaque data objects to represent various kinds of data used in computer vision. As mentioned earlier, they include images, image pyramids, arrays, scalars, distribution, convolution, etc. There are three most important features of these data objects that are important. The first one is the application gets only reference to objects, not the actual objects. These references should be released when the application doesn't need it anymore. The objects are reference counted, and object destroys an object. The OpenVX destroys an object when it is not needed anymore. So the actual destruction may happen later than the release call. OpenVX objects are strongly typed, which is good for safety critical applications. We would like to get some object-oriented behavior, but it is not supported well in C, and OpenVX is primarily a C API here. We get some of that having OpenVX objects really be pointers to opaque data structures, and because they are pointers, any object can be downcasted to VX reference, so the object can be used by generic APIs such as get status. So you kind of seen this example in the previous slide where you're calling get status after creating a context. So you can kind of downcast the VX context object into a VX reference in that. And third point is OpenVX objects are opaque, and access to the data content is explicit and temporary. The application first has to get access to the data, then it can use it, and finally do some kind of a comment. Now this gives OpenVX a chance to it's free to store the data in some kind of DSP local memory or dedicated GPU memory. It can do whatever optimization it needs under the hood, and implementation has a lot of flexibility because of this opaqueness in there. It also makes the code more functionally portable across various implementations. OpenVX API has both type depths and associated enumeration values for all data types. These include basic data types such as integers, floats, enums, and predefined structures such as rectangles, key points, and opaque data types such as image, graph, objects, etc. And these enumerations will be useful to create data objects and query data type of an object that will be used. We're going to discuss that later when we kind of create objects. I just want to mention that quickly here. And now let's look at some of the data creation APIs. For image, you use VX create image, and you kind of specify the width, height, and type of the image format. And there are about 30 different image formats. And to create an image pyramid, you call VX create pyramid. You specify a number of levels, what's the scale factor, what is the width and height of the base image, and the format of the image. And similarly, you have functions for creating arrays, lookup tables, remap, matrix, distribution. So you can kind of see the name is kind of very consistent, kind of very easy to intuitively figure out the name. Here is a simple example to start with. First, we create a context for the OpenVX operations in data. then we will start building a graph in that context. So create input image and output images, create a graph object, and then intermediate virtual image. We will never look at this particular virtual image because it's kind of intermediate, so it kind of gives a chance for the underlying framework to optimize certain things. Then add two nodes. First one connects the input to the intermediate image, then second one from intermediate to the output. Here kind of use the F1 and F2, just a kind of a placeholder. These F1, F2 can be image filters such as dilate or erode kind of operations. Now that this kind of builds the graph that is shown in the diagram below here. Once you think you build the graph, you kind of have to verify the graph to make sure there are no errors in the graph building, such as if there are no loops, the underlying framework get to check everything. It also gives a chance for the underlying framework to do certain optimizations, such as where to use tiling, where it can reuse memories, where it can fuse the kernels. All those opportunities will be available during for an implementation under the verify graph. Finally, you just process the graph in a loop. Kind of take an input, copy it into the input image, and then process the graph and read the output coming out of the image. It is that simple. And you can also have multiple graphs sitting inside a context. Right? This is kind of a simple hello world example. We're going to look at some more complex examples here. Right? Now that you've kind of seen how to create and build a graph, now let's start looking into built-in what are the various vision functions that are available, and APIs for accessing data objects for reading and writing, and so on. So there are 44 built-in functions in OpenVX 1.1 that I mentioned earlier. It has a bunch of pixel-wise, image pixel-wise functions here. You can see our basic arithmetic functions such as addition, subtraction, multiply. There are logical functions available. And there is magnitude and phase when you have a gradient available coming out of, let's say, Sobel operation. You can pass those gradients and compute magnitude and phase at a pixel-wise, pixel level. And then you have threshold, table lookup, color depth if you have to convert from 8-bit to 16-bit and vice versa. And if you have different color spaces like as RGB, you want to convert it to YUV or vice versa, you can use color convert. And if you have if you want to extract, if your application needs to extract separate channels from RGB separately, you could use channel extract. Or if you have separate images of RGB in U8, you can use a channel combine functionality to combine them and create a RGB image. Same goes with YUV kind of images too. And so accumulate functions are a little special in that if you kind of look at every other function, you have they all take inputs and outputs. Accumulate kind of takes a bidirectional data. So to say, for example, accumulate image is very simply as A plus equal to B. So kind of A is kind of bidirectional. Similarly, accumulate squared is just A plus equal to B squared. And weighted image is pretty used for alpha blending kind of applications. Well, let's look at some of the filtering functions that are there. So you have the basic box filter, dilate, erode, Gaussian, median, Sobel, and kind of 3x3 filters. And there is a general convolution function where you can pass a convolution object with your own kind of filtering coefficients there. Then there is a Gaussian pyramid functionality, which basically takes a input image and then output is going to be pyramid. Just when you can declare how your pyramid is. We're going to look at the example, a detailed example of that. And there is a nonlinear filtering. This nonlinear filtering got added in 1.1, which basically takes the, if you take the dilate, erode, and median we've seen the 3x3 functions. What nonlinear function does is filter does is kind of expands it to much broader, so you can have a bigger than 3x3, and you can also specify a mask, what set of pixels you want to kind of process in there. It's kind of a general function. And then there's Laplacian pyramid and reconstruction for computation photography kind of use cases there. Geometric functions. You can take an image, scale it down, scale it up. You can warp an image. and then you can also do apply a Gaussian filter, and then have kind of output is kind of half scale. It gets used in Gaussian pyramid, where let's say you have an image and you want to kind of apply a 3x3 or 5x5 Gaussian filter, but you're only interested in subsampled image of factor of 2. You could use this function. We kind of exposed it explicitly half scale Gaussian because we found a lot of applications would kind of use that. And there is remap, where if you don't have a standard, if you have a very nonlinear complex way of mapping input to an output, you could use remap. You can kind of compute a table offline and then pass that to the remap node, and remap node will just kind of perform that remapping operation for you. And there are certain reduction functions such as histogram, mean standard deviation computation, and min max, and the location of the min max in an image. And there are other miscellaneous functions such as scan edge detector, equalize histogram, fast corners, Harris corners, optical flow, and there's an integral image kind of functions. You can look at VX nodes.h to look at all the functions that are available and what parameters do they take as inputs and outputs. Yeah. So now let's look at how to access some of these opaque objects for reading and writing. Let's look at VX rectangle T, because this is kind of used to create certain other opaque data objects here. It's a very important data structure. It is used to specify a rectangle region inside an image. This rectangle T data structure contains a start location, which is the coordinate of the first pixel that is inside the rectangle in the top left corner, and the end location, which is the coordinate of a pixel that is just outside the rectangle in the bottom right corner of the patch, as shown in the picture here in the red color here. And then VX key point T, this is another important data structure which represents the key point. The most important field of this data structure are X coordinate, Y coordinate, tracking status, and strength. This will be used if you have a coordinate detector. We give an image and the outputs are going to be a list of key points. It can specify the X and Y and strength, things like that. And when you use optical flow, you want to track these key points, and you can have an array of these key points used for kind of optical flow kind of a functionality in there. If you notice, there is the enumeration VX type key point that we can use in some of the examples for creating an array. Now let's look at how to create an array object and access its data memory. Right? Use VX create array function to call function call to create a kind of an array. Then you need to specify type enumeration, kind of what kind of array element is that you want. You can specify type key point for a key point array, or you can also specify something like type UN32 if you want an array of integers in there. And you also need to specify the capacity, since you have to say what is the max capacity of this array is going to be. When the array object is created, it will have no items in it because kind of just got created. And to kind of query how many items are there in the array, you need to kind of query an attribute called VX array num items that we're going to discuss later. Here is an example to look at. To create an array and to hold 64 items of VX rectangle, we just call VX create array context, specify VX type rectangle, and then 64. To reset, let's say you already have certain items in the array. If you want to reset the number of items, you need to call VX truncate array, and then call VX add array item functions to add more. And to query number of items, you simply call VX query array and then pass VX array num items attribute, which kind of returns a VX size parameter that kind of gives you number of items in the array. You can access data memory of an array in two different methods. One is by copying the data into an application control memory or from an application kind of host memory using VX copy array range function. First, you have to make sure you query the num items before you're calling this function, because you cannot copy more than what is available there. And specify copy direction, whether you want to copy it from host memory to this opaque object or from opaque object into a host memory that is local to the application. You have to specify memory layout, which is kind of a stride across two consecutive array elements. Another method to access memory is by using map and unmap, very similar to OpenCL kind of functionality. You call map array range function and specify range of items to access and the direction read or write. It can be read write too. And this function returns a memory pointer and a stride and a map ID. Now that you have a pointer and the stride, application can kind of do read and write or both from that array. When done, you have to make sure to call VX unmap array range function with the map ID written by the map call. This kind of gives the pointer control back to the framework. It is important that you don't access this pointer after the unmap call, because that can lead to a lot of issues, because that pointer may not be valid, because it may be just depending on because of the range of hardware that OpenVX supports. The spec forbids accessing such a pointer after unmap. Now let's look at how to copy pixel data. It's kind of you can access pixel data one plane at a time in an image, and this is kind of very similar to how you conceptually the way you access arrays. There is a copy image patch function to copy a rectangular region of a image plane. For copying, you need to specify the rectangular region, the plane, and the direction read write, and you have to specify the layout of the application buffer that you have in the host memory using a VX image patch addressing structure. I'm going to show that in the next slide. And another way is you can request direct access to the pixel data using map image patch and unmap image patch. And very similar to the previous one, you just specify rectangular region, call a map, which will return a pointer in the memory layout of the pointer returned by the framework, and the map ID, and application just does all the read-write accesses that it needs, and then application needs to call unmap with the map ID that was passed. And again, you should not access the memory pointer once the unmap call is made. Now let's look at the memory layout. It is specified using image patch addressing T data structure. There are a number of there's a number of columns and rows, and there is xstride, which is in case of a single 8-bit kind of 8-bit image, it would just be 1 for the xstride, and that when you advance by 1 byte, you get to the next pixel. That's what the xstride is. For RGB images, which kind of densely packed, you would see that this xstride will be like 3 bytes, or sometimes a bit depending on implementation, it can be 4 bytes also, depending on the underlying implementation. And ystride tells you how many bytes you have to advance to get to the pixel row below, very similar to what you use in OpenCV kind of a scenario. And the scale and step are parameters used in subsampling images. And one thing to notice here is when you call copy patch image, the only fields that the spec requires to update are dimension x, dimension y, stride x, and stride y. And in fact, the most important ones are stride x and stride y, because that kind of specifies the layout of the buffer that is there in the host. Feature tracking example. So far, we have looked at how to create data objects, build graphs, accessing kind of data objects in and out. Now let's look at the feature tracking example to see that kind of using Lucas Canade optical flow algorithm to see what are the other features in OpenVX that are useful for much more complex example like optical flow. So you kind of need 2 sets of key point arrays and image pyramids. One set that corresponds to current time, another set that corresponds to previous time. And optical flow is kind of, you're trying to see where a key point has moved from an image in the previous time to the current time. You're kind of trying to track that key point. So now you need to keep track of an old copy of the pyramid and old copy of the key point, and the so the best way to do this is to use a VX delay container with kind of 2 delay slots. We're gonna discuss the details of the delay object. All it lets you is keep a copy of the current one and previous one, and after some time it lets you swap these two. So that way you don't have to do a physical memory copy, it just kind of shuffles the pointers around. You also need to use a Gaussian pyramid kernel to compute pyramid from grayscale to the input. This takes care of kind of building that tracking graph. So if you kind of see in this particular example, you're kind of taking an input is an RGB image, you're converting into a grayscale, and then you're computing a pyramid, and then you're running an optical flow, looking at the pyramid of the current image and the previous image, and looking at where the key points are in the previous image. From that, you're kind of computing key points in the current, where you kind of see key points at t equal to n, and stands for kind of now in there. And now that if you've kind of build a graph once you build a graph like this, we're going to go more detailed step by step in the next slides. You also need to initialize the key points for the first frame and corresponding pyramid for the first frame. So you can do that using another graph and using a Harris node, because optical flow doesn't create the key points, it just kind of tracks the key points. So you need another mechanism to create the key points. So we'll use an example to use Harris detector to create the key points here. Alternatively, you could use fast corners or any other kind of key point detector to do that. Now let's see how we can build this kind of application and step by step. So first one is pyramid object, which represents collection of related images. These images are created either by downscaling or upscaling base image contained at level 0. There are a few restrictions, including restrictions on supported image formats. You cannot have multiplanar images inside a pyramid in the current spec. And here is an example. You kind of create a pyramid by specifying number of levels, scale, width, and height, and format of the base. And the scale is kind of a floating point number. There's an enumeration for half and orb specified. You could specify any number, but most important one is going to be the half scale that we're going to be using in this example. And you can specify number of levels to be 2 or 4 depending on the use case. In the exact diagram that is shown here, there are 4 levels here. Once you create a pyramid object, it kind of contains within that a number of levels. Each one has a separate image. You can get access to individual images by making a function called VX get pyramid level, where you pass a pyramid level, a pyramid object, and then pass the level that will return an image object. Once you're done with using the image object, you can call VX release image. So the reason to call release image is just kind of reference counting, as mentioned before. Just release means that the application doesn't need the reference anymore, so that underlying framework can keep track of how many different modules are just accessing this particular image. When no other reference of this image object is needed, it can kind of freely release it. Delay object, it looks like it's like a ring buffer maintained by the system. Though spec doesn't say it as a ring buffer. I'm just kind of giving you a kind of analogy, so kind of make it easy to understand. This object can be maintained. It can maintain any kind of OpenVX data objects with kind of few restrictions. You cannot have a delays inside another delay. You can create a delay object by passing desired objects exemplar and number of references you need within that delay object. Here the exemplar object, exemplar metadata is used to kind of create new objects inside the delay object. It doesn't actually make the copy of the data. It just uses the metadata. For example, if I pass an image as an exemplar, it just looks at the image width, image height, and image format. It doesn't use any other information in there. The reason for taking reference as an input is so that we don't have to have separate function for create delay from image, create delay from pyramid, that kind of create a lot of set of functions that kind of simplifies it here. And we have a reference as a any object can be downcasted to reference. We have that feature in OpenVX. Here is an example for creating a delay of a pyramid. So imagine for the example that we have, we need to create a delay object with 2 pyramids. So let's say you create a pyramid with number of levels, say 4, and a scale factor of 1/2. You create a pyramid and you call that as an exemplar here. And then create a delay object passing the pyramid as an exemplar. Notice you have to downcast that to VX reference and pass number of slots as 2. And once you create the pyramid, that exemplar is not needed anymore. It's kind of a temporary buffer. So you can just release the pyramid object. Since the pyramid object is not referenced inside the create delay anymore, that then implementation can choose to kind of release the memory of the pyramid object. Once the object is, once you have access to the pyramid delay object, now you can individually look at pyramid objects inside the delay. You can use VX get reference from delay to access pyramid object at delay slot 0 or delay slot -1. And after processing each frame, typically you want kind of you want to do a timer tick. So you want to kind of take the previous current frame and keep it into the previous as a previous one, like in the example. You just do a timer tick. That kind of does a takes the objects to one cycle through kind of a ring buffer kind of a scenario here. Now, here is kind of a snapshot of data objects that we need, and in the feature tracking example. So you have a delay object of key points and a pyramid delay object of pyramids, and both of them have 2 slots in them, and you just kind of create a pyramid exemplar, key point exemplar, and using those exemplars you create delay objects in there. So now let's look at how to build a graph to compute the initial set of features using Harris graph. So we have the RGB input coming from a camera. To get a grayscale from RGB, first you need to convert RGB into some kind of a color format that has luminance plane. Let's say we use IYUV here. Then just use color convert node and channel extract node to get the grayscale from the RGB. You can kind of see the color convert node gets you to IYUV, and the channel extract node, you specify which channel you want from IYUV. In this particular case, it's going to be channel Y, and that gets you to the grayscale image. Then you just add Harris corner node function to get the key points directly from the grayscale. You do have to pass some additional parameters, such as Harris specific, algorithm specific parameters such as strength threshold, and what is the size of the gradient filter that you want to use. Those kind of parameters, I'm going to explain those in the next slide. And you also need to create a Gaussian pyramid for the optical flow of the next frame. And that's it. Once you're done with that, you're ready to process the first frame, and you can also use it later if you want to kind of refresh the key points after, because optical flow tends to lose the key points after running through some frames. So let's look at the API usage now. For RGB to YUV conversion, you call VX color convert node, and the second argument should be the RGB image. And the third one should be the intermediate YUV, which is a virtual image here. To get luminance channel, you call VX channel extract node, and specify the channel of interest, which is VX channel Y here. And now that you have 8-bit luminance image, you can run Harris corner algorithm using VX Harris corners node. This Harris corners requires parameters. You see on the left side there is a strength threshold, min distance, sensitivity, gradient size, and block size. I can give some kind of typical examples that we use in some of our tutorials here. In addition to that, you need to make sure that arrays that you create have enough size to keep the key points. So typically we kind of tend to suggest use 10,000 for the example that we have done in our tutorial. Now let's look at how to build a graph for tracking features using optical flow. It is important to note that virtual objects are specific to a graph, so that means you need to create another set of virtual images for the tracking graph. So while doing the Harris, you created virtual image specific to the Harris graph. Now, when you're creating optical flow, when you create a virtual image, you pass the optical flow graph as an object, as this kind of a scope of the virtual image here. You can kind of see the various nodes here for the optical flow. This is very similar to what we went through before. You need a color convert channel extract, and once you do that, you need to create a Gaussian pyramid to compute the pyramid for the current one. And then optical flow takes the current pyramid and the previous pyramid and the key points from the previous image, and then computes the key points of the current image. And once you have this kind of flow diagram ready, calling the CPS are going to be very similar to the way we did it for the Harris. Right? And the important thing is make sure you need to call VX age delay function after running the Harris graph every time, so that you have the current set of pyramid and key points get swapped with the previous ones. That way you kind of have a flip-flop happening between these two. So now that you know how to build a graph and access data objects, now let's look at how to execute a graph to process all the images coming from a video sequence. So before executing these graphs, you need to call VX verify and make sure to check for it is successful, and you do that outside the loop. And inside the loop, to process each image from the input video sequence, you just take the data coming from the camera, write it into the RGB image object, and then execute the graph. In this particular example, for the first frame, you want to run the Harris graph, and for second frame onwards, you just kind of run the optical flow graph. And once you are done with once you have the process graph written, you can read the key points from the current and previous using from the delay using VX reference from delay. You can access the current key points and the previous key points. You can read them. You can plot them on the output screen. You can kind of, depending on what the application needs to do with that. And then you need to flip the previous and current pyramids and key points using the VX age delay. And this will take care of triggering all the previous and current ones inside the graph automatically. And once you're done with processing your application, at the end of the graph, there is an attribute of a graph that you can query to see the performance in terms of how much time it took for running each of these graphs, in terms of what's the max time, what is the average. You can also query this attribute after running process graph every time, so that you can kind of keep printing how much time it took for every call. Right? Once you're done, you just release all the objects using VX release functions at the end. So this brings us to end of my presentation. In summary, OpenVX is a low-level C API that lets you access computer vision accelerator with both functional and performance portability. OpenVX contains three main components to make this happen. First, a library of predefined and customizable vision functions. Now we're calling them as kernels. And in 1.1, we went through the 44 most commonly used functions here. And second, a graph-based execution model, which enables kernel fusion, data flow, scheduling optimizations that Kari has alluded to in his presentation. And third, opaque data objects. This is very essential for functional portability. One has to use specific APIs to access the physical memory only when needed. And finally, OpenVX API is designed to be object-oriented. It defines execution model that supports both synchronous and asynchronous execution. In the example I took, I specified VX process graph, which is kind of asynchronous. So you make a call, as soon as the call ends, you know all the data output is available. There are other APIs such as VX schedule graph and wait graph that you could use to kind of for asynchronous operation. And you can also extend OpenVX functionality by using existing APIs. Through enums and callbacks, you can extend creating new functions. in there. Here are two links that are very useful. One is khronos.org/registries/vx, where you'll find the specifications. And you can also, on the Khronos, access links to existing implementations. There's a discussion forum that you can participate. And there's a sample implementation from Khronos, and you can also access implementation from commercially available implementations and open source implementation. And I put one more link here for OpenVX tutorial that we've been using for the past 1 year. That's it. That ends my presentation here.
Excellent. Thank you very much, Radha. That was wonderful. So we have about 10 minutes left, and we would love it if you guys would go ahead and submit some questions if you have any. We've gotten some questions from one person. I'll turn this over to Frank, and he can answer the question we have. And again, in the meantime, go to the question mark icon on your tool, and you can submit questions to us. Thank you. And let me unmute Frank. Okay, you're on, Frank.
Hi, my name is Frank Brill. I work at Samsung, and there were some questions that were put in the chat window here during the call about availability and when does it run on Android and things like that. So, so if you can actually download the sample implementation today, and you can build it for Android. It has been tested on Android, and we expect that the first implementations will probably come from vendors. So if a particular vendor has got a device, they will ship it with an implementation. And as we get more of those, I would expect that it would become part of the standard API for Android, but it's not as of today. So, and there was some questions about who's got implementations today. So you actually they're publicly available implementations. AMD has an implementation today that you can download from them. All of these are available. The links to these are available actually on the Khronos site if you go down into the resources area for OpenVX. So AMD has a publicly available open source implementation. There's also, if you get the VisionWorks library from NVIDIA, that also has a OpenVX implementation in there. So those are available now on those devices. The AMD uses both CPU and GPU, and the NVIDIA also uses CPU and GPU for acceleration. There are some other that have been other companies that have passed, but their implementations haven't been made public yet. So we have to ask those companies actually what their plans are. But the expectation, I would think that there will be more publicly available implementations this year and early next year.
Resources per page lists also synapses and imagination, so I guess those are available. So that would make it for commercial or open source implementations available now. Yeah, there was also a question about whether it's likely that Qualcomm would release something next year. Well, none of us work for Qualcomm, so we can't really speak for them. But Qualcomm has been very active member of the working group from the beginning. So I would assume that they have some internal developments ongoing, but we don't know when they're ready to release or ship.
And did you guys see the other question that I posted?
Graph node parameters fixed, or can they be? They can be changed. So the question was: are the graph node parameters fixed, or can they be time varying to accommodate relaxation? Yeah, so there are some parameters that you pass to the nodes that are basically like fixed after you create the graph node, and those are usually kind of normal, like C ints or floats or something. But then there are some many nodes take on other parameters that are like VX float or VX int, and those parameters can be changed after the graph is constructed. So you might change, for example, the sensitivity. Like if you use Harris corners, like in the Radha's example you did to do some tracking, you could, if the level of light, for example, changes, you might want to change the sensitivity of the corner detection. You can do that without having to recreate a new graph. So some of the parameters can be changed, but some of them are fixed at the construction time.
A follow-up question, can a graph be a node?
Yeah, that's an interesting.
Well, there is a functionality to sort of encapsulate a graph, and so a developer can create a graph and then create graph parameters, basically the inputs and outputs to that graph, and that graph could be saved in a separate library, and then that could be used by a third party who can link to that library that defines the graph, and without knowing anything about the internals of the graph, they can use the inputs and outputs to it. So to that third-party user, that graph looks like a node.
Does anybody else have any questions for us?
I want to mention about the previous question about changing parameters. One is the one answer that Kari gave is about changing certain parameters such as thresholds and things like that. And there is other one. Let's say if your application has buffers, various images coming in multiple buffers, there is a function called VX create image from handle, which lets you you have data coming in various buffers, so you can kind of asynchronously just swap the buffers, and there is an API for doing that very efficiently. If you have a live data coming from a camera coming into, let's say, 2 or 3 buffers, you can kind of in real time kind of switch the buffers and then run the graph again, switch the buffers. So while one picture is being captured, another image can be processed using the graph, and that will be a very useful functionality.
We do have one more question. It says, how granular is the performance measurement? Only on the whole graph or on each individual node?
So we do have attributes to query graph as well as the node for performance. So we have nodes also have an attribute for querying the performance. In terms of how accurate it is depends on implementation, but I think the units mentioned are in nanoseconds. So the API lets you query node level and graph level performance in nanosecond units.
Yeah, one caveat to that in terms of when these graphs get optimized, it could be the case that nodes get merged or even eliminated if the graph optimizer is able to do that. So in some cases it's difficult or impossible to give a an exact node level timing information. So you can get that information from the graph, but you should know that sometimes it will be vendor dependent as to what comes back from that sometimes because of those various optimizations.
Another question, once the image is processed, is it easy to continue processing of the output data in OpenCL?
Yeah, it should be possible. I mean, the images come out as just data, so you could pass it to your OpenCL shaders, and some implementations may even allow you to write your user kernels in OpenCL. So we didn't much discuss about user kernels today, but you can write your own kernels, and it's a little bit kind of implementation dependent in which languages you can do it. Every implementation probably supports C, in which case it could run on devices that can compile C, like CPU, but some implementations might also support OpenCL, which could run both on CPU and GPU. And if you do that, then you can schedule your own user node as part of the graph, and then the kind of graph manager would also manage the data passing from kind of built-in OpenVX nodes to your user node that could be implemented in OpenCL. Those are some possibilities.
All right, well, we have... Go ahead.
Yep, I wanted to extend what Kari has mentioned. In addition to being able to specify a user node in OpenCL, you could also create an image from using an OpenCL memory handle. And again, these things are going to be vendor-specific extensions, because if you try to look at OpenVX API, it is designed to address all kinds of hardware, from DSPs to GPUs to CPUs to some fixed function hardware. So you kind of have to look from the scope of your application, what kind of hardware it uses. You cannot expect a functional portability of using OpenCL and expect it to be running on a fixed function hardware. That may not happen. But if you know exactly what kind of, if you're using GPUs and CPUs, and if that's what is within your scope, yes, it is possible to create user nodes using OpenCL code, and also letting an implementation give you OpenCL output buffer or take OpenCL input buffer, and then being able to, your application can further continue processing on the same OpenCL buffers.
All right, well, thank you, gents, for this presentation. This was very interesting, and thank you to the audience for submitting questions. An email will go out to everybody shortly that has the URL where you can go to get the video of this presentation. Also, you can download the OpenVX reference guide and also a PDF of this presentation in your GoToWebinar panel. All right, well, thank you very much, and we look forward to seeing you at future webinars. Thank you. Goodbye.